we're going to start this with a definition, and you'll note right away in the definition that we have an uppercase f and a lowercase f, and that's just to say that the two functions we're talking about are related to each other. A function uppercase f is called an antiderivative of lowercase f on an interval I if uppercase f prime of x is equal to lowercase f of x for all x in I. We aren't really going to be concerned so much with the interval. We're concerned with this relationship that uppercase f prime of x is equal to lowercase f of x. Suppose I tell you that f of x, and I'm using uppercase of course, is equal to x squared plus 3. Then you would tell me that f prime of x is equal to 2x. Likewise, if we were looking at f of x is equal to like x squared minus 7, then you would say that f prime of x is equal to, again, 2x. And something like f of x is equal to x squared plus pi has a derivative f prime of x equals 2x. And you're starting to get the idea that the answer keeps being 2x, right? And the reason for that is, of course, the power rule. The derivative of x squared is 2x according to the power rule, and the derivative of these constants is 0. And that brings about an issue with antiderivatives. If I start by saying, hey, f prime of x, and by the way, this would be the lowercase f of x in this scenario. If I say f prime of x is equal to 2x, and then I ask you, hey, what is f of x, the antiderivative? You could tell me that f of x is equal to x squared, and then I'd say, yeah, but what about all these? The plus 3, the minus 7, the plus pi. The answer here is that uppercase f of x is equal to x squared plus c, where c is an arbitrary constant. Why is this? Well, remember that the derivative of a function at a point gives me the slope of the tangent line at that point. Here what we're looking at is the graph of y equals x squared. And I've drawn a tangent line here at the point where x is equal to 2. And as you can see, if I take the parabola and vertically translate it, then the slope of the tangent line at that point doesn't change, right? And that's all these numbers are, right? This plus 3, the minus 7, the plus pi, these are all just vertical translations. So what we get when we find an antiderivative is actually a family of functions. And when we write down something like f of x equals x squared plus c, what we're writing is the most general antiderivative. And this leads us to our first exercise. Find the most general antiderivative for the function f of x is equal to 6x squared. Now let's recall the power rule for differentiation. d dx x to the n is equal to nx to the n minus 1. This is true, but I want us to think about this in terms of like steps. In order to differentiate x to the n, what I'm going to do is I'm going to write the n as a coefficient, and then I'm going to change n to n minus 1. I want to turn that into some formal mathematical language. When we write n out front as a coefficient, what we're doing is we're multiplying by n, or a little more generally multiplying by the exponent. And then we subtract 1 from the exponent. Suppose I want to reverse that process. I'm going to go in the opposite order, and I'm going to do the opposite operations. So I'm going to add 1 to the exponent. I shouldn't do that. There. And then divide by the new exponent. In the case of this lowercase f of x equals 6x squared, I'll say uppercase f of x, right? That'll denote the antiderivative, is equal to, add 1 to the exponent. I start there. So I'm going to write x cubed. There was already a 6, and then divide by the new exponent, so over 3. Don't forget our constant because we're finding a general antiderivative. The answer is going to be f of x is equal to 2x cubed plus c. Yeah, this isn't quite so bad. As you may recall from a previous video when we first saw derivatives, if I have a position function s, then its derivative s prime is the velocity of whatever's moving, And the second derivative, s double prime, is the acceleration of whatever is doing the moving. It follows directly that if I know acceleration, then one antiderivative will give me velocity and another antiderivative will give me position. So for falling objects, acceleration is constant. And in the US system, acceleration is 32, I'll say feet per second squared. Actually, I can clean this up just a little bit. The acceleration due to gravity is 32 feet per second squared in the system used in the United States. And in most of the rest of the world, acceleration is the acceleration due to gravity. G is 9.8 meters per second squared. For something flying through the air or falling, the only acceleration they experience is due to gravity. And so we can start out with a constant a of t is equal to 32. Then the antiderivative v of t is going to be 32t plus, ordinarily we would say plus c, some arbitrary constant, but we're going to say plus v sub 0 because, as it turns out, when time is t equals 0, the only velocity you have is what you start with. So v sub 0 is initial velocity. And the way we got from a to v, anti-differentiation. And then for the position function, s of t, we're going to use the power rule. So we're going to add 1 to the exponent and divide by the new exponent to reverse what we would do for differentiation. 16t squared plus v naught t plus s sub 0, and s is an initial height. To verify that this is the correct position function, we can differentiate. We'll see we get v, differentiate again, we'll see we get a. In the rest of the world, a of t is 9.8, so v of t is equal to 9.8 t plus v naught, and then s of t is 4.9 t squared plus v naught t plus s sub 0. If we were on some other planet or the moon or something, this number 32 or 9.8 would change, but this whole process would not.